Hello, I'm Mike Grubb. On behalf of the Southern Gas Association and all of our 160 plus member companies, welcome to SGA's Architects and Engineers virtual conference on removing barriers for energy efficiency. We are pleased to have with us today 4 highly qualified experts on building for energy efficiency. George King is with Apache Corporation, which is one of the top 5 independent producers in the United States, and he's going to talk with us today about hydraulic fracturing. One thing is certain, we have a lot of interesting and important information to share over the next 3 hours. So let's get started talking about the plain facts of hydraulic fracturing with George King. George is Apache's Distinguished Engineering Advisor. He is a registered professional engineer in Texas and in Oklahoma with 42 years of experience. George's technical work has provided advances in shale developments, environmental risk reduction in well construction and fracturing, sand control reliability, and underbalance perforating. He has taught fracturing and completion courses for 11 years at the University of Tulsa. George.
Thank you very much. And today what we'll be looking at is some of the history behind hydraulic fracturing and well construction from an environmental risk standpoint, what we've done to reduce the risk and what we're doing to continuously improve the risk so that we can have this great supply of natural gas into the future. The history here goes back over 70 years, and it evolves the invention and development of hydraulic fracturing in the 1940s and 50s, and then the development of new methods of fracturing, and finally the marriage of horizontal wells and hydraulic fracturing in the 1970s and 80s. By the early 1990s, we had done over 1 million hydraulic fracturing jobs in North America, and over the last 20 years, we have done another 1 million jobs, mostly in horizontal wells that have multiple fractures along the length of the horizontal. This whole technology has been driven by a desire to produce more gas from shales. This is a primary method of getting the gas where it was originally evolved. There is a long history. The first gas shale well drilled in the 1820s in New York. And over the period of time, really starting about 1975 to 1980, there were a number of people that really pushed the envelope on adapting technologies and even inventing some new technologies to where the recovery of gas has risen from 1% of the gas in shale being actually recovered for use to now it's 15 to 45% recovery depending on the shale itself. New technology advances are taking that further into a better recovery. The first thing we need to look at is in well construction, and it has to do with safety. Many things have been said about wells leaking, and various very high percentage of wells have been really said to leak. But when you look at this, you have to remember that wells are constructed with multiple barriers. And these barriers, if one fails, the barrier behind it will catch it and contain it. This is simply a barrier failure. It is an indication that we need to change something in the design, but it is not pollution. To get pollution, you have to have all the barriers fail. You have to have pressure in the well higher than the pressure on the outside of the well, and you have to have a fluid that will actually flow through the leak path. Fortunately, in well development and production, we're continuously reducing the pressure inside the well, and that gives us an advantage. But what we're looking at in terms of detail is how many barriers we need in a certain area of the well. The maximum number of barriers are coming when we need to actually protect fresh water or any usable water from any kind of contact with either fracturing fluids that we're pumping or the hydrocarbons that we're producing from the well. Starting about 3 years ago, I actually looked at hundreds of thousands of fracs looking for problems and failure incidences. And risk here is really measured by how frequently an event occurs and the impact of that event on our ecosystems. What we found was hydraulic fracturing posed essentially no risk. But our definition of hydraulic fracturing is just the pumping of fluids into the ground during a 2 to 4 hour period for an individual frac. When you look beyond that, some other people's definition of hydraulic fracturing is everything from drilling to the production of the well. So there is a confusion in definitions to start with. What we found in our studies, though, was the transport of materials to and from the well posed a minor risk. The rest of the development activities, including construction and fracturing, posed very little. This was driven home by a set of papers and some work on nearly 4,000 wells, where microseismic, a method of actually measuring the very tiny sounds of rock breaking, was tracked during about 3,800 wells that in 4 individual shales. Now, the interesting thing about that, you plot the top of the fractures against the deepest fresh water there is. The closest approach was about a half a mile away. So are we fracturing into groundwater? No, we're not. That can only happen with the very, very shallowest applications, and even then, it's very difficult. However, in deeper wells, it is a very, very remote possibility if it exists at all. Now, these fractures, as can be seen in this particular slide, are very narrow. This is a downhole television camera picture from the 1970s, and this downhole TV pictures have been around since the 1960s, and we have been measuring frac direction, frac width, and frac height with these in open hole formations. And again, we have problems getting a frac to even go up as much as 300 feet. They are naturally limited by your barriers within the rock itself, your stresses in the rock, and the leak off of fluids that are being pumped into this larger area of contact with the formation that the fracture forms. Dropping back from fracturing and looking at well construction, we see that the cement becomes the main seal from the pipe to the drilled hole. And this is some work done in the 1990s at Amoco. What it showed was in zones, very high pressure zones like Matagorda in the Gulf of Mexico or Tuscaloosa in South Alabama, that if you had even 50 feet of cement, that you could stop 10,000 to 12,000 psi pressure differential. Now, we use 300 to 600 feet of cement as an overlap, and many strings are cemented clear back to the surface. So cement is important, but the placement of that cement to make sure all of the other zones are even more important. The oil industry goes back well over 150 years to the 1820s in New York and to the very, very early 1900s in Oklahoma and in Texas. And in that meantime, Pennsylvania got to be some of the biggest oil producing areas in the world. But as these eras have changed, we have gotten progressively less polluting. From the early days of cable tool drilling, where we didn't have cement in the wells, to the 1900 era, where cementing was rapidly improving. The blowout preventer was invented in the 1920s, and rotary drilling replaced cable tools in the 1930s, ending the spray of oil up over the top of the rig when they drilled into the oil zones. So all of these have had effect. Fracturing actually reduced pollution potential since it required less wells to develop an area, and it forced operators to use stronger pipe and more cement in their wells. Recently, we've been looking at well integrity and other issues, so era by era, technology has driven the improvements. We went back and looked at over 300,000 U.S. wells, Oklahoma, Ohio, several other areas, and basically what we found was the older wells had a much higher failure rate, even up to maybe 0.1%, which is considerably below what you hear people saying that wells leak. But when you look at it in depth, the integrity failure, that is all of the barriers that are failing and a leak actually happening to the outside, that's extremely rare. And in one recent study, 16,000 horizontal multi-fractured wells were surveyed without finding any leak at all. So if we're not really adding to the pollution, where is the pollution coming from? Now this graphic is from the EPA in 2000, and these are the most reported issues in that 2000 EPA document on water quality. And they are from underground storage tanks from neighborhood gas and diesel stations, agriculture, and municipal effects. Really, oil and gas industries don't even make the list. Some of the shallow injection wells coming in at, say, number 17 on this list were actually industry disposal wells from other types of industries. So when I looked at this, I wanted to know, since that was in 2000, what does it look like today? So I took 11 years of data. I used Texas as an example simply because we've drilled over 1 million wells. We have 250,000 wells on production, have done over 500,000 fracks, and underneath Texas is 29 major and minor aquifers that really speak for about 90% of the Texas land surface. Through this have gone 1 million wells. Now, if we saw indication here of pollution, we'd see it quickly, simply because Texas is number 2 in groundwater withdrawals. So we're just not seeing that, particularly when municipalities and agriculture account for over 80% of what we withdraw. These are the last 12 years of pollution reports and what the materials are. It's still a lot of gasoline and diesel fuel leaking from old tanks or that haven't been remediated. The rest is from agriculture and industry. Oil and gas wells don't make that list again in the top 20. If you do look for oil and gas activities, what we found is that most of the issues are around surface leakage, pipelines, tank batteries, truck filling stations, etc., near surface small spills. When we looked at gas, oil, and injection wells, they barely made any type of a list, most often not even reported as a problem at all. So when you look at failure frequency, you look for the type of well, one of the biggest things that we see is the maintenance culture of the operating company and how they take care of their wells. In addition to that is the era of construction, because that specifies the technology that was in use when these wells were created. We went into the Gulf of Mexico, pulled all the records from the actual leakage of wells up until Macondo from 1980 to 2009, and we found that the average amount of leakage in these wells was somewhere between 3 10,000ths and 5 100,000ths of 1% of produced oil actually leaked out. And that is in very small quantities here. Macondo was an outlier. Still, it was something that our industry learned a lot about. Now, gas migration is a big issue in many cases, and the real issues around this are geographical location and the quality of the regulations that dictate both oil and gas wells and water wells. There's over 15 million water wells in the United States, most of them not built according to any kind of regulations. This is something we have to look at. We want to make sure we don't add to this problem. Now, the methane seepage, There's 1,100 natural oil and gas seeps on the North American continent, and these mainly drain down into the Gulf of Mexico. So we have to be sure here that this natural problem isn't added to by the oil and gas industry. Now, this is a chart on comparing the spills and the seeps with production itself. And on this list, the 3 oil field leaks have been from drilling wells. The rest of them are from pipeline incidences. Literally, we don't have much of a problem from producing wells themselves. And if you look towards the bottom, you'll see in red the seepage volumes that come in from natural seeps and some very small accumulations of oil spills from cars and boats, etc. That adds up to about 1/4 of Macondo volume flowing into the Gulf of Mexico every single year, and most of that has been flowing in for centuries. Now, how much water do we use? We're looking towards water sustainability. We're trying to get away from fresh water almost entirely. Apache has really led this way, and in most of our operations are using 40% to 100% of recycled produced water as our frac fluids. And we've got a lot of effort going on in this area. Now, on water issues, one of the issues that we need to watch is the time period right after fracturing when we're bringing a lot of waste fluid back. Most of your waste water is recovered within the first 5 days. This is usually hauled off location. Afterwards, we have the water and the gas going into facility operation, which separates, captures the gas, rejects the water that's either re-injected or formulated into new fracturing fluid. So where does the produced water go? It can go into oil field brines that are disposed of, but primarily are being injected back into water flood operations and recycled into frac fluid. We look at disposal as being a last resort and a limited option. We support regulations, and we think this is an excellent plan, but there are regulations that improve standards and get everyone on a consistent basis, and there are regulations that are proposed by people who just want to stop the oil and gas production. We differentiate here. I won't read these, but you can see some of the examples between the two. Now, what additives are we using? Initially, some of the service vendors wouldn't identify their additives. To counter that, what Apache did was to come up with a list of those chemicals that we do not approve of pumping, and these included the endocrine disruptors, the carcinogens, the highly toxic materials. We put those on a list on our website, and our operators that work for us cannot pump those on our wells. This is an approach that we really feel is valid. We also support putting all of our information on the Frac Focus website. Now, here are some questions that I would ask. I want green completions. I want to see us limit that development activity to areas where it is least disturbing. And then do the basic site investigation, test the fresh water wells that are in your area, and look at your water sustainability. How can you make that better? So problems, we look at some transport spills, we look at technology eras that define the leak rates. We're trying to do a better job, and what we're finding, the safest well is this horizontal well that is multi-fractured, because that replaces 5 to 10 vertical wells. It can reduce your development footprint by over 90%, and we've done over 1 million fracs from these horizontal wells in the industry. So what is the bottom line here? The risk of groundwater pollution from producing wells is very, very low, and barrier failure rates and the well failure rates do vary widely. So the rest of these things, we're seeing some real advantages. We're even working with air emissions during and after the job. We're using diesel engines where At least 60% of the diesel has been displaced by cleaner burning natural gas, and this has reduced significantly the amount of emissions from the pumping operations. And this is where we have tried to get to. Mike?
George,
I'll
well,
turn it
thank
back
you.
over.
Well, thank you very much. I appreciate that very much.